but now the load can be controlled by the electric motors and the vehicle inertia as opposed to just the vehicle inertia and the operator throttle position. So now what we have is the engine is spinning at 2,500 RPM continuously. The electric motor, when the vehicle is at a stop, would have to spin a negative 1,000 RPM to allow for a net gear ratio of 0 so that the engine can free spin and the vehicle doesn't move. And then as you accelerate, the engine stays constant, the electric motor will increase in speed, and that will in turn increase the vehicle speed. And the x-axis here is vehicle speed, and then this is the component speed, whether it's the engine, the final drive, or the electric motor connected to the ring gear. Engines, like I mentioned before, consume a quantifiable amount of fuel even when the vehicle is not moving. And this is because the engine only makes power during the expansion stroke. All of these other cycles consume power. And what happens is the energy that we get from the expansion stroke, we store some of it in a flywheel to then return that energy back into the system to draw in the new fuel, to compress it, and then that energy is also stored to force the exhaust gas out. So if an engine is stopped, it can't just suddenly start running. We have to use some type of starter actuator to start the engine. And when the engine is sitting there at idle, depending on the size of the engine, it can draw anywhere from 6 to 12 horsepower. So when you're stuck in traffic or you're stuck at a stoplight, you're consuming fuel even though you're not using it for anything. Well, with this design, because we have a variable engine speed, we have a variable transmission gear ratio. We can shut the engine down at low speeds and low power requirements and only run off of electrical power. We could use energy stored in batteries or supercapacitors or, like I said, a fuel cell, and you can actually run the vehicle as a pure electric vehicle. You wouldn't have to run the gasoline engine at all. So now what happens is, from 0 to 15 miles an hour, the engine is actually not running at all. The electric motors, both the one connected to the ring gear and the one connected to the final drive, are creating all of the acceleration torque. Once we reach a certain speed, then the inertia of the engine and the power coming from the electric motors can start the engine, and because they're all mechanically connected, the electric motor speed has to drop, and then the engine and the electric motors can continue accelerating the vehicle. But this allows you, for low speed, low power applications, you don't have to run the engine, and you can conserve fuel. One slide?
17, slide number 17.
Number 17.
Now here we are locking the speed at 2,500 RPM. Assuming the rated speed of the engine to be, say, 4,000, what will happen when the requirements of power are there and the load is there? How will we manage that extra power?
You can either divert it to the batteries if the batteries aren't fully charged, but if the batteries are fully charged and we can't divert that load, then we have to drop the engine power down into the less efficient range. And that's when a powertrain engineer could make the determination, okay, my batteries are charged, I don't need that much power, I'll just shut the engine off. And I'll run on electrical power only until the power requirements are increased or the battery levels are decreased to a certain engineered point.
So there's some complicated force strategy for power management.
Yeah. So what we're doing is, instead of having a big V8 engine that can supply a whole lot of power all the time, we're now taking a look at the entire operating usage of a vehicle, because like my truck with a V8, I can drive it 250 horsepower all I want, but then when I'm going down the highway, I'm probably only consuming 60 or 70 average horsepower. So I can look at the overall usage of the vehicle, and I can figure out what the average power is and try to find a gasoline engine that might produce that much power or maybe a little bit more, and then I can just use my battery and power management so that when I really step on a throttle and I need to get out of someone's way, the power is there. But the amount of power that I'm consuming by the engine, because it's smaller under lower power requirements, I'm able to conserve fuel. Okay, and we just talked about this one. There are more sophisticated methods for hybrid CVTs available. You can connect an electric motor. You can use any combination of sun gear and planetary gear sets that you desire. Some have more advantages, sometimes where you can actually lock up both motors and just run off of engine power. There's a lot of different designs out there. Some, like I said, some have advantages. You have more weight, you have less weight, you have more torque available, less torque available, depending on what the application needs. I mean, you could connect this electric motor to the sun gear and put this planetary gear power to the ring gear. It's all depending on what you need and what your application is. The conclusions. Hybrid technology combines the energy density of gasoline, which is typically 42 megajoules or 44 megajoules of energy per kilogram, with the efficiency of electronic actuators. Because typical electric batteries, a lead-acid battery has about 40 kilojoules of, it's about a scale of 1,000 times less power energy per unit of weight than gasoline. So personally, I don't see gasoline or any type of internal combustion going away for a while, but this allows us to use the efficiency of electronic actuators with the energy storage capacity of gasoline. And as these components, the electric motor controllers and the electric motors themselves and the computer algorithms can control the controllers, as that usage increases, or as those component costs decrease, you'll see more and more hybrids. And I believe that the new era of fuel efficiency will come from recovering the wasted heat energy and the wasted mechanical energy of an engine.